Thank you. So in the last class, we have seen the stop and wait basic working principle with a different analogy, and then we have seen the stop and wait model as well, correct? And we have calculated the maximum effective throughput as well as the effective transmission rate, correct? In today's class, uh, we will study the transmission efficiency on error-free channel and transmission efficiency on error channel. And if time permits, I'll take the sliding window protocols, that is go back in, and the selective repeat ARQ protocol. Right. So the first topic which I'm going to introduce right now is the transmission efficiency on the frame the sender is sending to the destination will be reaching 100% without any error. So that's the meaning of this model, right? And in the last class, we have calculated the effective transmission rate as well as the maximum effective throughput, correct? And the transmission efficiency on free error channel that can be denoted using the notation called the neta. And here I cannot use the neta. So what I will do is I will write just efficiency. It's a ratio of R effective, right? Last time we have calculated, right? Here it is there, no? R effective. So that is the NF minus N0 divided by T0, means the total number of bits in the frame minus total number of overhead bits for header and CRC or checksum error detection technique to the total time taken for transmitting a one frame successfully, right? That we got the transmission, the effective transmission rate, correct? So that is the RF divided by R. So this is the, so where R is the channel transmission rate, correct? Now we know the R effective, right? So R effective is what? NF overhead NO divided by overhead, correct? So this is the T overhead, right? Or this is the T0, not overhead. This is the T0, right? And total divided by the transmission rate of a channel R, correct? And if you arrange in the proper order, so we will get NF minus N0. Sorry, this is not N0, N overhead, correct? Divided by total time taken to transmit a frame successfully into R into R, correct? And we know the T0, right? T0 at the beginning only we have calculated here. This is the T0, no? So this is the complete T0, right? So that I can put here. What I'll do is to F minus N0 or N overhead divided by, so it will become very small. So I'll take here and put the divided by, because the T0, it's a very big equation. So I'm writing like this, NF minus N0 divided by 2 times plus 2 times T processing time required and the ratio of NF to R, correct? Overhead are the acknowledgement bits divided by R, correct? To whatever the R, this is R, right? So this R only we will be writing here. Right? So we got NF minus N0 and T0 is this complete equation and whatever the R we are having, that is the R, correct? Okay. Now we need to divide by NF on numerator and denominator, NR and DR denominator, right? So what we will get is so NF will get cancelled. So 1 minus overhead divided by NF, correct? 1 minus N overhead divided by NF, correct? So I'll make like this. Okay, I'll paste this one here. So here, so divided by, this is complete divided by, so I can make it as, so I'll rewrite this one so that you'll get a clear idea. So yeah, NF, see 1 minus N0 divided by F, right? Yeah, so NF divided by R, correct? And I have divided the NF. So I'll write here NF divided by NR plus NA, correct? Divided by NF into R. So 2 I'll be taking out and I'll be writing T plus processing, correct? Into R. And as we are dividing by NF, so what I will do, divided by NF, correct? So in this case, so here, right, in this NF divided by NF into R, correct? So NF will get cancelled and here also one R is there. So this will be the R, here will be there R. Here R will be there because this is the R I'm saying. This R I'm saying, correct? Inside it will be the multiplication, so R will be there, correct? So Na by R into NF by R, correct? So this is how we will get. So if you again reorganize, then NF into R divided by NF into R, it will get cancelled. It will be 1. And this R will get cancelled. So we'll get NA divided by NF plus 2 times, right? T propagation plus T processing R divided by NF will be there. Correct? So that I'll be rewriting as this one. Anyway, that's 1 minus N overhead divided by NF. Correct? N overhead divided by NF whole divided by. So I'll put here and I'll bring this one there so that you will get a clear. Yeah. And this one I'll just cancel this so it will become 1 here, and this R will get cancelled and this R will also get cancelled. So I'll get 1 plus Na divided by Nf into T propagation plus T processing Rf, right? So if you see this equation, this part Na divided by Nf, or what you can say NO divided by NF, right? So earlier here I have written, right, N0. So this is the RNO. It is the number of overhead bits for header and CRC. So same thing I am writing here. So this is the effect. You can write it as here. This is the effect of frame overhead bits, right? That's the reason this term is coming 1 minus NO divided by NF, or number of overhead bits divided by total number of bits in the frame. Right? So this is the overhead of effect of frame overhead bits. Right? Similarly, you are having in the denominator one more term called this NA divided by NF. At the beginning, I have declared few notations are here. NA, that is the number of bits into the acknowledgement frame, right? So this is the overhead of acknowledgement frame. You can write acknowledgement overhead bits, correct? And this overhead bits and the acknowledgement overhead bits, right? So these are very less compared to the actual actual number of bits in the frames, right, as well as the bandwidth and the propagation or processing delays. For that reason, we can make this as 0, right? So I'll make this one as the 0. So I'll write this one as a 0 here. Sorry. So this is the 0, correct? Similarly, this term here also, it's a very negligible term. So for this also, I'll be writing it as a 0. Right? So remaining terms, that is 1 divided by 1 plus T 2 times T propagation plus T processing into R divided by NF. So this is what? This is a complete bandwidth of the channel, right? So of course the R is the transmission rate of the channel, and this is the delay involved during the transmission of the frame, correct? So this I can write it as, I'll write this efficiency 1, okay, 1 1 divided by, so I'll make a small this one. So efficiency equal to 1 divided by 1 plus what we got 2 times T patient plus T processing into right R, correct, into R. I'll write one more here. I want to define one more term. So that's the reason I'm in detail writing here. Divided by what is the one more term? This is the NF. This is the NF. Correct? NF. So this is the actual efficiency of the stop and wait model during the error-free channel, right? So this again I'll be defining a one term here. So I'll be calling it as a D, and D equal to round trip time into R divided by RF. RTT, round trip time. At the beginning only I have told round trip time means the time the sender is the time taken by the sender to transmit the frame, actual data frame, and receive the acknowledgement frame from the receiver. So whatever time it takes, right? So this time we call the round trip time. In our case, we are having already the round trip time has the 2 times T plus T processing. Correct? So in I can rewrite as the efficiency formula. Correct? As the 1 divided by 1 plus. So 2 times T propagation is the RTT, right? RTT. RTT. Anyway, I have written there. So it's just like 1 plus D. This whole term 2 times TR propagation plus T processing, right? I'll get this complete from this, correct? So this is not RF, this is the NF. So this is the actual formula for calculating the efficiency of the stop and wait protocol during the error-free channel, right? So let's take one example. Let us consider round trip time is 30 milliseconds. 30 milliseconds and NF. So total number of bits in the frame is equal to 12,000. And the R, that is the channel transmission rate, is 1 Gbps. Now anybody can you calculate the what is the efficiency using the formula? Everything is ready now. So we have to just put it into these formulas and get the efficiency. What is the efficiency? Students?
So could you show the slide once again?
Yeah. First calculate the D, that's all. If you calculate D, then efficiency you can calculate, right? And for calculating the D, you are having this expression. D equal to RTT. You know the RTT and you know the R and you know the NF. So how much you will get?
0.998.
0.9998. You need to tell in the bits per second. So if you calculate, so it will come around 400 kbps. Okay, so this is the efficiency you will be getting. So actually, so you can understand here, I'm having the channel transmission rate 1 Gbps, but I'm able to use the only the 400 kbps. So it's a not a efficient method to employ in the real time scenario. Correct. So this is the reason in real time we are not using the stop and wait protocol for transmission of the frames. We are using the some other ARQ protocols we will be seeing in future slides. Okay, so now the second uh, calculation of the efficiency, that is stop and wait in channel with errors. So in the previous we have seen without errors, so 100% successful of the transmission of the bits at the transmission of frames from sender to the receiver. So here we need to consider the with errors, and the errors in the channel randomly they can occur. So for that we need to use the probability theory. So for that we need to define uh, some parameters, that is let be the probability that a frame transmission has errors, and 1 minus PF the probability that a frame is without errors. You can rewrite this also of probability that a frame is with errors. And minus PF is the probability that a frame arrives without errors. Correct. Now, the average number of transmissions to first correct arrival is 1 divided by 1 minus PF. So now we'll calculate the average total time taken per frame or successful. So in the earlier case, we were having the T0, correct? So that T0 we have calculated here. So this is the T0 total time to transmit one frame successfully. Right? So we are having that one. But here with the error, we have considered errors. So here we need to consider the probability of a frame arrives with errors or without errors, right? So that is like here T0 divided by 1 minus is the average total time taken per frame for successful transmission. Efficiency during the with errors channels, right? So whatever we had the previous formula, that is the R effective divided by R. What was the R effective? R effective was the total number of bits in the frame minus total the overhead bits in the frames. That is the NO, right? And divided by T0. This is the right. This is the one. But here we are having T0 into 1 minus PF. T0 1 minus PF and divided by this is a complete divided by R. Correct? You can refer back here. Here, efficiency R effective divided by R, and R effective we got it from NF minus N0 divided by T0 and divided by R. So same formula we are using, but here the average total time taken per frame for successful transmission is T0 divided by 1 minus PF. So yeah, here I have made one mistake. T0 divided by 1 minus PF. So NF minus N0 divided by T0 divided by 1 minus PF whole divided by R. Right. It has NF minus NO into 1 minus PF. Correct? 1 minus PF whole divided by the same formula was that 0 into R. Correct? T0 into R. Again, you can check back here. We got the same, right? NF minus N0 divided by T0 into R. Correct. So same thing we need to put. So whatever the value we got the T0. So this T0 we need to write it here. And again we need to divide by NF, right? And finally, what we will get is the so final efficiency formula I will write here. Load, which we have done it in the before. So finally, what we will get is 1 divided by 1 divided by 1 plus t. So this is the one we will get. Along with that, one more factor we need to consider here, that is the 1 minus PF. So this is the only difference we are having compared to the previous. So in the previous one, we have got just 1 divided by 1 plus D. So this is the efficiency formula we got. And we have not considered the errors in the channel. So now we have considered errors in the channel. So whenever we calculate the efficiency, we need to consider that factor as well. right? So that's the reason here we have the effect of errors in the channel. So this is the effect of frame loss or errors in the channel. That's the reason we have writing that factor here. Correct? So if you take the some factors, the PF sum value, and you if you use the same example which we have done, right, and you will get a clear distinguish between the efficiency with errors and without errors. Correct. So far what we have done is we have calculated the efficiency with and without errors in the channel, right? So this is the one way to improve the efficiency of stop and wait protocol. But efficiency still we have not satisfied. So as per this previous example, we are having the 1 Gbps transmission rate of a channel, but we are able to send or we are able to use only the 400 kbps, very less. So it's a completely inefficient the stop and wait protocol. So how to improve the stop and wait protocol efficiency? So one way what we can do here is, see, if you see these formulas, right? So only one factor is always, giving us some impact in order, in order to improve. So that factor, what we call is the NF, right? So NF is the number of bits in the frame. So I need to increase the more bits in the frame, correct? And that is not easy for us, right? So NF is calculated depending upon the MTU, right? Maximum transmission unit in the data link layer, right? And in the transport layer, we use the maximum segment size, right? So depending on that only we can determine the NF, but randomly we cannot increase. So it's a not a good idea to increase the number of bits here. Correct. So what else we can do it? One way of doing or improving the efficiency of stop and wait protocol is like this. See, in these scenarios, the stop and wait protocol, just I need to send a frame and wait till it it receives the acknowledgement from the receiver. Correct. So only one bit it can send. It cannot send the more than that, right? Suppose if you increase the window size, sliding window we call. So sender and the receiver will be having here. Here I have put on box, right? So this is the one box, right? So this is the only one box, and this box contains the information or the frames of the sender. Similarly, here also I will be having the 1 bit window. Here I have written, right, single bit window protocol, alternating bit 0 and 1. Though the sender is having more than one or more than two number of frames, but the sender is incapable of sending those frames until it receives the acknowledgement of the previous frame, right? So F0 it has sent and it is expecting the next frame called the EA1. So that's why the one is there. And F1 is sent and it is expecting A0, right? So one at a time it can send. Suppose if I send the more than one number of bits, so what will happen then? So that's the one where we will come into across the one more protocol called the go back N protocol. So let's study the next protocol or the windowing protocol called the go back. Go back N protocol. So here we are having the window concept. Window size means the number of frames have not got any acknowledgement from the receiver, right? And how to calculate this window size, right? Window size, how to calculate the window size? Window size will be calculated depending upon the number of bits we will be using for sequencing the frames, right? In the earlier, what we have done only one bit, right? 0 or 1. Here we can use any number of bits, right? So the window size is equal to is to n minus 1, where n is the number, sorry, number of bits used for sequencing the frames, right? For example, n equal to, what will be the window size for this? Window size equal to 0 to 2 raised to 2 means 4 minus 1 equal to 0 to total. I'll get how many? 4. This is how we'll be going to calculate the window size of the go back N protocol. And here one more important point here is only the sender will be having the window size. Okay, whatever the bits we will be using here, only that number of bits window size will be there at the sender side, but at the receiver side, whatever the mechanism or the whatever the concept we have used in the go back N protocol, that is the only one window concept will be used in the go back N protocol, right? Let's see one example. You will get a more idea about that, right? So here I'll be writing the window size. So 0, 1, 2, 3, 4, 5, 6. And I have considered n equal to 2 bits, so total 0 to 3, right? So what I will be doing is, sorry, I'll put this in the window I'll say, and this will be like this. This will be like this. So this is the window size equal to 4 bits, or you can say window size 2 bits, 0, 1, 2, and 3. Similarly, at the receiver side, so how it will be, as I have mentioned earlier, it will be having only 1. Okay, so very important one, carefully listen. So whenever the receiver receives the frame and the receiver sends the acknowledgement for that frame, that time only this window, the source window, will be shifting. That's why the name called the sliding window protocol. And once the receiver will receive that frame, so this receiver window, right, will be sliding into the next frame. So that indicates that the receiver will be accepting the 0th frame. So here in this case, the receiver will be expecting the 0th frame. So frame, suppose sender will be sending the frame F0. Correct. F0 it has sent. Now, receiver what it does is, now the receiver will shift the window. So already it has received the frame, right? Anyway, it will check all the errors and everything is fine. Then it will shift to the next. So the receiver will be expecting the next frame, that is the F1, right? So what the receiver will do after receiving, so it will be sending the packet frame, right? Suppose it is sending here A1. So this is, say, for example, caps A1 has sent here. And this indicates that this window, it can send the till 3 packets without any acknowledgement received. So next packet will be sent like this. So this is the F1. Now what it does, it will shift the next, right? F1 has received this. So next will be F2, correct? And this will be receiving here. So acknowledgement, it here it will be coming. And suppose F2 it has sent, correct? F2 it has sent here. Then the receiver, now it will be expecting the next frame for the F3, right? So till here I'll be having the same sequence, correct? So I'll write here so that you will get a clear idea. So this is the point, and here also the same. So window has not moved to the next, correct? And F3 it will be sending here. So maximum it can send F3, right? Because the window size is F3 here. So this is the F3. But unfortunately, the F3 won't reach here. It will be lost. I'll write here. F3 will be lost. Correct? So I'll write this one. This is the A3. Right? And I have told in the earlier class, right? So it will be starting the timer, right? So it will wait till its time period, correct? And at this point, right? Next at this point, so this window, now it will be shipped like this. Like this it has shipped because it has received the A1 acknowledgement, but here it won't send the F1. Here it will send the next packet. After F3 it will be F4. Here F4 will be coming. Very interesting one. You can just listen. F4 here. But here, very interestingly, receiver, right? Receiver will be waiting for F3. F3 has not reached here, but waiting for F3. But F4 will come. So it won't accept the F4 because it will be expecting the F3. That's the reason this packet will be lost here. Similarly, here, if it will be assuming that, okay, before that, here, right? A2 has come. So now it's time to slide, right? So that's the reason he can send the F5, but still he cannot succeed because receiver is waiting for F3, correct? And has the receiver has or the sender has received the acknowledgement A3, right? So it will be moving. Select. And this guy can send the next frame F6 because F6 is in the window, right? But the receiver won't accept because it will be waiting for F3, right? So these all three frames, right? These three frames, though they have correctly received, but these frames, the receiver will be ignored, right? Will be ignores the receiver because it will be waiting for the F3, right? So at this point, this F3 has lost it. Timeout has happened here. So this is the timeout. I have not written here. This is the timeout for F3. Timeout of F3. After this, it will start sending the F3. This is the F3. Now this receiver window will slide. Waiting for F4, right? So this is the F3 is the retransmission. So I'll write here retransmission. And again, yeah, anyway, it has not received any kind of acknowledgement. It will be waiting. Now it will send the acknowledgement. So I have received the F3. So please send the F4. Right? Then it will send the F4. Oh, sorry. So it will send the F4. So again, F4, F5, X6 will be sent back. So F4, F5 and F6 will be sent. So students understood how this works?
Yes, sir.
Yes, sir.
Okay, good. But can you identify the problem involved in this ARQ? Can you
Sir,
tell
is
me
it
what is
delay at the receiver?
delay at the receiver? No. No. See here, this part ignores the receiver and saying, though the receiver is receiving the proper packet or without any error packets, F4, F5, F6, still it is ignoring because it doesn't have any buffer or any storage here. So that's the problem in this case. So this, in order to solve this kind of a situation or this kind of a problem, they have come up with one more solution or one more protocol called the third protocol, selective repeat ARQ protocol. Right. So here what happens is both the side. I'll just take this part so that I can show you only one simple example. So I'll select source, time and window. So here what happens is, so whatever the window size was having in the sender, the same window size will be there at the receiver. So if you keep like this kind of a scenario, then we can solve these retransmission of these F4, F5, F6. Correct. even though it transmits F4, F5, F6, and even the receiver will be having the same window, it will definitely it will accept the all the frames. So the name why it has come the selective repeat is only the selected frames will be retransmitted. That's the one. So whatever we are having here, suppose you, if you think this is the one, wait, I will take the entire thing. Yeah. If you consider this one, so this one I'll just delete all. Same situation, but it doesn't ignore. So whatever the windowing size was there here, same thing will be there here also. Right? So F1 will be there and F2. It will be receiving, and F3 anyway it will be lost, right? So but in the window size we will be having F3, F4 as well, correct? So yeah, I'll down this also down. So you can easily see F4 it is sending after lost, this F3 is lost, F4 has sent, right? F4 has sent. So here the window size will be the, in the window F4 will be there, so it will accept. And here F5, right? So it will accept because in the window the F5 frame will be there, so that's why it will accept. And here F6 will be there, the window, so it will accept. So same thing, right? Correct. But retransmission, whenever this acknowledgement will come, right? So suppose this acknowledgement will comes here, then only the lost frame acknowledgement will be. So selectively, so for example, here, right? So this acknowledgement comes before the timeout of F3. So this acknowledgement contains the A3. That's the reason we have mentioned that selective repeat ARQ protocol, only the selected frame will be retransmitted, not all, right? So A3 will be there and F3 will come. Then here onwards, again it will start F7, F8, F9, like that it will start. Okay. So let's stop the class now. So if you are having any doubts, you can ask.